Hi, my name is Shivdath, and today we're going to look at a very interesting and tricky problem. Without further ado, let me just state the problem. We have a 100-storied building. So, this building has 100 floors on it, and we have two eggs. Egg A and egg B. And the impractical scenario of this problem is that these eggs, we really have no idea at what floor, if we drop them from, they would break. So it's very possible that they may not break if you drop them from floor 100. They may break if you drop them from floor 1. They may break starting floor 35 and onwards. So we really can't tell. But we do know that the two eggs are identical, and that if they break at, say, floor 31, then they will break all floors above. So there is a starting floor at which they break, and then they break if dropped from any floor at that floor or above that floor. So the question is, how many tries do you need to be able to find the exact floor at which the egg will break? So if you want to think about this problem, pause the video, go ahead, and think of different ways you may attack it. Alright, so right off the bat, the first kind of thought is, a first thought that may come to your mind is, how can you predict the exact floor? Can you predict the exact floor with two eggs, or can you just get a hunch? Well, clearly you can predict the exact floor, because you could predict the exact floor with one egg, because just say you had one egg, you dropped it from floor 1, 2, 3, 4, 5, so on, till it breaks at floor X. X is the answer. Meaning you can take up to 100 tries that way, so you can clearly get an answer. But what's the optimal answer? What's the minimum number of tries you need to get the floor at which an egg would break? Just the fact that you're given two eggs makes it seem like you could do better than 100, because with one egg, the optimal and the worst case would be 100, right? You keep dropping for 1, 2, 3, 4, and in the worst case it won't break till it gets to floor 100, in which case you had 100 tries. It may not even break at 100, but you would have to throw it from 100 to get to know that. So, but now we're given two eggs. How can we make this optimal? So let's take another guess. What if we drop an egg from floor 50? So right from the midpoint of the building. What if we dropped an egg? Well, now there are two cases. But let's just, one case is if the egg breaks, right? If the egg breaks from floor 50, what can we conclude? We really conclude that the floor we're looking for is between 1 and 49, right? Similarly, if the egg doesn't break, we conclude that the floor we're looking for is in the upper half from floor 51 to 100. So really that's dividing our building into two sets that we can choose to focus on. We've divided the problem in half. It's just like binary search, when you divide the problem in half and then tackle the correct half you want to deal with. But now we have two eggs, and let's say it did break at 50. Then what do you have to do? You have one egg left, and the best you can do is check from floor 1, 2, 3, 4, 5, 6, 7, like that, up to 49, which is 50 tries. So that would give an answer of 50, which is better than 100 if you just started dropping from floor 1 and carried on. But can we do better than 50? If you want to think about this a little bit, now is a great time to pause the video. Alright, it turns out, yes, we can do a lot better than 50. And a good way to get through that is perhaps by doing a little more trial and error and seeing if a pattern develops. But let's try and be more general. Let's notice that let's suppose that n is that optimal minimal number of drops that we need to find the correct floor. So we need n drops. Now notice that basically if the first egg breaks, whatever floor we drop it from, let that optimal floor be whatever, x or something. If that first egg breaks, then as we've seen from some examples we looked at, really the only choice for the second egg is to go from 1 up till that, and up till n minus 1, right? So in other words, A breaks implies B goes 1, 2, n minus 1. In other words, the first egg, egg A, would really have to be dropped from the nth floor if you require n turns at best, because you need n minus 1 turns for B. So that's a very interesting idea. Similarly, if the first egg drops on one's second try, right, then you'd have n minus 2 drops available for the second egg. So let's look at kind of a realistic example with real numbers, and try and generalize this idea. Let's say the optimal number was 15. Let's just kind of take a trial and error guess and say 15 was the number of drops you need. And just kind of pull that out of a hat. You could do it with any other number and try and generate a pattern. So basically, if the first egg breaks on the first try, right? Then really what you have is 1 turn actually sorry, I'm saying n is equal to 16 for the calculation that I wrote down. So if the egg really breaks on the first try, and remember we determined that if the number of tries is n, then you have to drop the first egg from the nth floor. So this would correspond to dropping the first egg from the 16th floor. So if the first egg breaks, right, you have 15 tries for the second egg, from 1 to 15. So that would be 1 to 15 turns. Now what if egg A breaks on the second try? Right? Then the first try is gone. The second try was egg A breaking. And since we have 16 total tries, you have 14 left. So in other words, if this was I'm going to make another column called floor. So this was the 16th floor. Now I only get to add 15 to the 16th floor because one try went on 16 and didn't break. One try went on the next floor, which I'm trying to figure out, and it broke. That one is here. And I have 14 remaining tries to get to 16 in total. And so that would be 16 plus 15, which is 31. 31 floors. And similarly, we can keep carrying this calculation out. 1 plus 13 if it breaks on the third try. That would correspond to 31 plus 13, which is 44. 31 plus 14, sorry, which is 45. We keep adding numbers in the row. And so on, till we get to 1 plus 9, which would give us to the 91st floor. And then finally 1 plus 8, which would get us to floor 100. So now notice in this pattern, right? We could have done this for any n. We chose n equal to 16, pull that out of a hat. But what would be a way to optimize this? Pause the video and think about it for a bit if you like. In this pattern, you see this is constantly decreasing. These ones are constantly the same. These intervals the interval between these numbers are getting smaller, just as these are getting smaller by 1 every time. How can we optimize this to make the number of tries as few as possible? Yeah, exactly. So the idea really, if in a computer science terminology, is really the first egg is helping us do a binary search. It's helping us divide that building into chunks, right? Into these big chunks, either 16 or 31 or in between, either 31 or 45 or in between, and the chunks are getting smaller and smaller by 1 every time, or 91 or 100 or between. And the second egg is used to do a linear search. It's now kind of the chunk size are going to be decreasing by 1. But what we have control over in this, if you look at this side, is to ultimately make the size of the linear search 0. In other words, at the last step, the linear search should be 0. Otherwise, we kind of overcompensated. We don't want to have. We want to kind of get this number down to 0 at the last step to get to 100 or above 100. That would make it optimal. So in other words, what we're really saying is that if we call this number p, right? What we're really saying is that 1 plus p plus 1 plus p minus 1 plus 1 plus 0. We want this number to ultimately get to 0. Should be greater than or equal to 100. Because that's the total number of tries. So in other words, now if we represent, now what is 1 plus p? 1 plus p is nothing but n, right? In this case n was 16 and we had 1 plus 15. So 1 plus p is nothing but n. So we could rewrite this as n plus n minus 1 plus 1 is greater than or equal to 100. Or this is just the sum of the first n natural numbers. So n into n plus 1 over 2 is greater than or equal to 100. And how do we solve for this? Well, you can solve for it, but you can also just try some heuristics, some guesses. What if we take n equal to 15? Or n equal to 15. 15 into 15 plus 1 over 2. 15 into 16 over 2. That's 15 into 8, which is definitely greater than 100. It's 120. What about, so 15 would work. What about 13? We would have 13 into 13 plus 1 over 2, or 13 into 7, which is 91, which is less than 100. So let's check 14. 14 into 14 plus 1, 15 over 2. That's 15 into 7, which is 105, which works. So that gives us n equal to 14. And that's our answer. It takes 14 tries to determine with 2 eggs precisely the floor at which an egg would break, which is quite a bit of an improvement above 50, which is really quite a first guess. It's less than third as much. And so just to recap, basically if the egg breaks on the first go, then we take 1 plus p turns, where p is n minus 1. If it breaks on the second go, right, to get to n total turns, we would take 1 plus p minus 1. And summing these all together should be greater than or equal to 100, the number of floors. Solving for n gives us n equal to 14. I hope you enjoyed it. Thank you very much.